All right. So, sinusoidal input frequency response, lecture 6.4. We're getting into some really cool stuff here. And the book and these notes are diverging a little bit at this point, the Rowell and Wormley book. Most of the same ideas are in chapters 14 and 15 of Rowell and Wormley that we're presenting here, but they might not be in precisely the same order. Slightly different ideas and presentation here, but most of the ideas are there. So if you get confused about what they're talking about versus what we're talking about, let me know, but I like this way better. So we introduced before the frequency response function, right? Oh, now we're going to start using it. So in this lecture we explore the relationship, which turns out to be pretty chummy, between a system's frequency response function, h of j omega, and its sinusoidal forced response. Okay? So sinusoidal forced response. I mean, I know we're getting pretty jargony here. We try not to get jargony, but we do kind of require it a little bit. So a sinusoidal forced response is the response of the system due to a sinusoidal input, right? Sinusoidal forcing. And we've looked at this before, right? We've looked at the sinusoidal response when we were solving differential equations. We could put in a sinusoid and we could solve for what happened. But now we're interested to understand the relationship between that sinusoidal forced response and the frequency response function, okay, h of j omega, which we've not explored before because we just defined it. So, yeah. Previously, I hadn't done a derivation of this. This is the most derivation-y we get in this class. This lecture right here. It's going to be pretty awesome. I had never seen this derived before, so I was like, ooh, I'm going to derive it. And like 2 or 3 passes on my whiteboard, and I finally got it. So, it helps when you know where you're going. You can find a way there easier. So, okay. So let's build the frequency response function. Let's build from the frequency response function h of j omega definition. So y of t is, by definition, the inverse Fourier transform of y of omega, right? So I'm using, there's a little bit of a notational thing here to notice. Even though sometimes we switch back and forth, so I mentioned the j in there being kind of a weird thing. I'm going to try to restrict my use of that notation to just the frequency response function, h, okay? So the frequency response function gets a j in there. The other Fourier transforms, I'll just say of omega. We'll see how well that holds up. You'll see a mixture of this. You'll see some textbooks, everything is j omega in there. Sometimes they're just omega, there's no j. We're going to try a little bit of a mixture where we recognize the usefulness of using the j for the frequency response function, but other Fourier transforms, it doesn't make a ton of sense to use that. So that's why we're doing that. So y of omega is the Fourier transform of y of t. So the inverse Fourier transform of it is y of t. So inverse Fourier transform of, instead of y of omega, we just plug in from the definition of h of j omega, which is just that it's equal to y over u. We can say that y is equal to hu, right? So plug that in. There's a start. Now, we have already our y of t. We have our h of j omega in this formula, so we're on good footing already for this derivation. We want to know what y of t is when our input is a sinusoid, and we want to keep h of j omega around. Okay. Preferably, we don't want it inside a Fourier transform or an inverse Fourier transform, but we're going to take what we can get. So we'll see how it goes. U of omega, the Fourier transform of the input, is in there, and we're specifically not just going to use any input, we're going to use a sinusoidal input. So we take it to be sinusoidal with amplitude A, angular frequency omega naught, and phase psi. So U of t is equal to A cosine omega t plus psi. So this can represent any sinusoid, right? Because you can have a phase shift to turn this into a sine, right? Pi over 2 phase shift will get you there. So you can get a sine out of this or cosine. So this is in general, any sinusoid with any phase and any amplitude. The Fourier transform of the input, U of j omega, a j snuck in there, U of omega, can be constructed via transform identities from table C2. So remember table C2 was the Fourier transform table. Okay, so let's take a look. Let's see, do I still have that up? Yeah, cool. So our Fourier transform table, remember it's got all these identities for the time domain versus the Fourier transform or the frequency domain. So there are 3 that we're going to use here, and we're going to construct. So it was actually, there's a little bit of work to make this 629 show up in the table precisely. So what I had to do is I decided to break it down into 3 different functions of time and show the corresponding transforms from the table. So just like really taking it slowly, because when you have to use 3 on the same expression, it can get a little confusing, right? So let's break it down, take it kind of slowly. So the first is that we have a scaling in the time domain. So this A here scales a function of time, and so that shows up in the table. So we'll talk about that one. Another one is that we have this time shift, which is a little subtle. We have omega naught t plus psi. So you can actually rearrange this to look like a time shift, which also shows up in the table. Okay, so we use that one. And then finally, we have another function, which is cosine omega naught t, which is the cosine function. So we've got those 3 functions of time that are brought together into one expression. Okay, and we're going to break this down and do the Fourier transform table identities for each of these. The t naught here, if we're going to say this is the case, is going to be minus psi omega naught. We're trying to write this as a function of t minus t naught, right? And t has a multiplier, omega naught, on it, right? And this psi shows up over here without that omega naught on it. So we can't just do a simple t minus t naught. We have to factor out this omega naught from both terms. So we end up with the omega naught being pulled out, t, and then it's going to be minus negative psi over omega naught. And now we've got a t minus, and then this is our t naught, right? It's a little subtle. I thought about just glossing over that part, but I realized that that's the part that everybody gets hung up on, is the detail of how to do that with the table. So that this derivation gives us a little bit of practice using that table. It shows up in the table as just a t minus t naught. We had to transform it into a t minus t naught. In order to do that inside this omega naught, inside this function cosine, we had to factor out omega naught and get that to be the case. So that's what we did in 6.30. And now we can look up the corresponding Fourier transforms from the table. So the first one is that the Fourier transform of P of t is going to be P of omega. It's going to be equal to A times Q of omega. So this was the good old-fashioned scaling which shows up, well, it's actually this first line. So if your A2 is 0 and you just focused on the A1, F1, you get A1, F1. So if you scale your time domain, you scale the frequency domain. So that's what we did in this first one. We used that identity. The next one is that if you have a time shift in your argument here, then that's the same as multiplying by e to the minus j omega naught, or omega t naught. So if you go to the table, we find, oh, here's our f of t minus t naught, so a time shift. That corresponds to just multiplying your Fourier transform by e to the minus j omega t naught. So that's how we got this next one. Q. Okay? So there was our next one. And then finally, we're down to our r of t, which is just cosine omega naught t, which fortunately does show up in this table. So it's this one. This one might deceive you. So it's not that one. It's down here. Cosine omega naught t, which corresponds to, whoops, these two Dirac deltas. Okay, at omega minus omega naught and omega plus omega naught. So now we've got our three transforms, and we can put them together to get u of omega equals, so we have an A from there, a pi that shows up from each term there, and then we are going to go ahead and just plug in, we could also say e to the minus j omega t naught, but we're going to distribute that to each term. So e to the, we're going to plug in our t naught, e to the minus, or e to the, it becomes plus because our t naught is negative, right? So e to the j psi omega over omega naught times delta of omega minus omega naught plus e to the j psi omega over omega naught delta of omega plus omega naught, and that's the end of it. So why did I distribute this? Because this term shows up both places, right? E to the j psi omega over omega naught shows up in both terms. It's because we're going to recognize this nice little identity here, which is delta is going to be 0 whenever its argument's not 0, right? So it's only important to know what happens when omega equals omega naught for this term, and when omega is equal to negative omega naught for this term. So we can rewrite this to be a pi, and since this gets zeroed unless omega is equal to omega naught, we plug omega naught in there, the omega naughts cancel, and we get e to the j psi delta of omega minus omega naught plus e to the, now this is j psi, omega over omega naught shows up again, and this time when omega is equal to negative omega naught, then it's the only time that's important for this delta. So the negative sign, negative omega naught. The omega naughts cancel, we get the negative sign still. And we get a delta of omega plus omega naught. Okay? So, now we're ready to substitute this into 628. So, what we've been doing is deriving this u of omega, right? So now we're ready to plug in for u of omega. And our y of t is equal to our u of omega gets inserted there, h of j omega. And we pulled out things that are not functions of the frequency. We're going to integrate. Remember, the inverse Fourier transform is an integral over the frequency, omega. So if it's not a function of the frequency, we can just pull it right out. So that's what we did. A pi, and we get the e to the j psi, e to the j, and minus j psi. The Fourier transforms. The only thing that gets left in these inverse Fourier transforms are the deltas, right? So the deltas from here and here remain. Everything else came outside of the inverse Fourier transforms, because this is the only thing that's left that's a function of frequency. But remember, oh yeah.
What did the deltas signify?
So those are the Dirac delta functions, so impulse functions. So remember, we have that sort of weird definition where they're 0 everywhere except for at time equals 0, where they're undefined, but they're like kind of represented as a peak there. And they have area of 1 if you integrate it over them. And one of the nice properties, remember last time we talked about the sifting property of the deltas. So when you integrate over something with a delta in it, it's real easy. So that's what's going to save our asses here too, is we're going to integrate over these delta functions, get rid of them, and also get rid of the integral while we're at it. So let's, so our 632, it looks like we're in a bit of a quandary here because we have this h of j omega. Remember, h of j omega depends on the system, right? So you might think, well, we're not going to be able to integrate over this until we actually know what h of j omega is. However, with these Dirac delta functions come in, and they simplify it big time for us. So, oops, that's what we do. So the definition of the inverse Fourier transform allows us to rewrite 632 as 633. Remember, it's just an integral definition. This is how I caught the error in the inverse Fourier transform formula from the previous lecture, because my derivation was coming out wrong, and then I finally traced it back to that. So we have these integrals, still with these deltas in there, recognizing that delta is an even distribution, which is to say that delta of t is equal to delta of minus t, and applying the sifting property of delta allows us to evaluate each integral. So remember, when you do this evaluation of the integral, whatever the sifting property says that delta of we have to change this to be minus omega naught minus, let's see here, no, omega naught minus, I should say, omega naught minus omega. That's fine to do. We can switch the order of those because we can take the, because it's an even function, so you can negate the argument and it stays the same. Just like if you had the function f of x equals x squared, which is an even function, and you wanted to know f of minus x still equal to x squared, right? Doesn't matter because it's an even function. Same on both sides. All right. So then we use a shifting property. So remember, all we need to do is just take the omega naught and plug it into these functions, and that's the integral. That's what the shifting property does for us. So this is what's left. We still have the e to the j psi's and e to the minus j psi. The e to the j omega t becomes e to the j omega naught t, and the e to the j omega naught t in this one. When you do this, notice that we have a negative sign here in the that's mixed in. So one argument is negative, the other one's positive. So we have to use a negative omega naught. So that's where this comes from. And h of negative j omega naught. So that got way simpler from 33 to 34, right? The integral went away, the delta functions went away. Using that shifting property, we really simplified that. So if we write h in polar form, catch up on my notes, we can say that y of t, so remember, h is just a complex number, right? So, well, it's a complex function, but we're evaluating it at a specific frequency, omega naught, right? So omega naught is a specific frequency. So Siri thought maybe there was something going on. So this is now just a complex number. So you can represent a complex number in polar form or rectangular form, right? So it's either a magnitude in phase or as a real and imaginary part. So either one's fine. So let's do that. So y of t, I give myself a little more room. Y of t is equal to, so the a and the over 2 thing is still there. A magnitude of h of j omega. I can't factor that out yet. Sorry. My bad. For those of you writing in pen, this is probably not the first time I fooled you, so I think that means shame on you. I don't know. George Bush forever screwed me up on that. So I don't know anymore. Somebody's to blame. Shame on somebody. Okay. Y of t is equal to a over 2. So this e to the j psi, so we still have the j psi, e to the j omega naught t, j omega naught t. This we can write as a magnitude times a phase, right? So magnitude of h of j omega naught e to the j, and then we would do the angle of j omega naught, so as a magnitude and a phase. Oops. And then we've got our other term, so plus e to the minus j psi, e to the minus j omega naught t times the magnitude of h. So the magnitude of h of j omega and the magnitude of h of minus j omega is the same. Okay. So we don't have to worry about that. We can just use the same h of j omega. And it's omega naught also. E to the, and we don't know on this. So this is the angle. So this is e to the j angle of h of minus j omega. So let's think for a second about what that is, omega naught. Okay, so we're getting somewhere, but let's remember for just a moment, in case we've forgotten, that the magnitude of h of j omega naught is just going to be the square root of the real part of h of j omega naught squared. So it's the root sum of the squares, right? Plus the imaginary part of h of j omega naught squared, and it's the square root of the whole thing. And then the phase is, of course, just the arctangent, right? It's just equal to the arctangent of the imaginary part of h of j omega naught divided by the real part of h of j omega naught. And if you forget this, it's totally fine. Just draw the complex plane, real, imaginary, and this is your angle, and this is your magnitude, right? The length of that. So you can do your trigonometry. You can use Pythagorean theorem to find the length of it, and then you can use trigonometry to find the angle. So, in case you forget what these are. Okay, so we're getting there. Now, the angle of h of negative j omega naught is the conjugate. Well, we can simply take the negative of the angle instead of the negative of the argument. And so we can pull this negative sign out. So we can rewrite this, and now I'm going to factor out the magnitude of h of j omega. So now we're going to start getting simpler looking. And now we're going to multiply this by a fraction, and it's not going to be obvious at first why I put the 2 under this, but it'll become clear. So we're left with one big exponential. I'm going to write exp because there's so much in the exponent that I don't really want to write it up in a little subscript. So, or superscript. So e to the j. So we have a psi plus, you add the exponents, right? Plus omega naught t. Then we've got this h of j omega. Let's see, well, 1, 2, 3. Okay. Plus this one just has a minus sign out in front, but it looks exactly the same. Psi plus omega naught t plus the angle of h. Whew. Okay. So that is, besides being a big mess, that is a sort of familiar expression. We notice that this phase right here, I'm drawing the line above it, this phase and this phase are the same. These are x, the e to the j that phase and e to the minus j that phase. This might ring a bell, an Euler's formula bell. So we're getting close. We're getting very close. So if we, oh man, I skipped this step, didn't I? Dang it. You guys, I wrote down essentially this one already. Got ahead of myself. pretty much this identity here where I pulled out the minus sign, that is due to the conjugate symmetry of the Fourier transform. Okay, so you can look that up. That's a hyperlink in the PDF version. Don't try to click it now. So the PDF version is a hyperlink that takes you to a discussion of the conjugate symmetry of the Fourier transform. So, which is to say that f of negative omega is equal to the conjugate of f. So conjugate. So if you had, for instance, f of omega, just to like try to ease this awkwardness. If f of omega is equal to a plus jb, then if you wanted to know what f of minus omega was, then you would say, oh, it's equal to f conjugate of omega, which is equal to a minus jb. So the conjugate is you invert the sign on the imaginary part, right? You guys did this then back in the day, conjugate. Complex conjugate. And you're like, I'm never going to use this. Imaginary numbers, when are they useful? Now. It's fine. Yeah, I remember people were always saying, this is stupid. We're never going to use imaginary numbers. I may or may not have said that too. It's hard to say. I sounded like that, that's for sure. So stupid. Oh no. It's almost spring break, yeah. Okay, so we got down to this. And this kind of looks like a mess, but like I said, this term, well, actually I can underline it now. This term and this term are the same. We have this e to the j that and e to the minus j that divided by 2. Euler's formula for cosine, do you guys remember it? I never remember it either, I have to look it up. Cosine theta is just equal to e to the j theta plus e to the minus j theta divided by 2. What? Yeah. So exciting. So that means that we've got cosine here. We've just got cosine. All this ugliness is just our familiar cosine. So, I'm going to this is like a big summary box, deserves a box equation. So just reminding us how we got here, for a cosine omega naught t plus psi input to system h of j omega, which is to say system with frequency response function h of j omega, the forced response is y of t equals a, so the original amplitude shows up. Makes sense, if you increase the input amplitude, you're going to increase the output amplitude.
Good job.
H of j omega I would say we got your back, but I don't know. We'd have to see how big he is. Okay, so we scale that input amplitude by a magnitude of h of j omega naught. We get our cosine back, omega naught t, plus psi. We get our old phase back, our input phase, and we just add the phase of the frequency response function at that frequency. So this is pretty awesome. It's a very remarkable result. For an input sinusoid, a linear system has a forced response that is also a sinusoid. So we weren't guaranteed that before we got into this. So like we put in a sinusoid, you get out a sinusoid. So that's cool. It's at the same frequency as the input. Notice the frequency of the output is omega naught. The frequency of the input was omega naught. Same frequency. It differs only in amplitude and phase. So the only difference between the input sign and the output sign is that the amplitude changes and the phase changes. And it's different in amplitude by factor of the magnitude of h of j omega naught. And it's different in phase by the phase of j omega. So actually specifically evaluated at omega equals omega naught, right? At the frequency of the input. So that's very remarkable. I mean, this is something that we talk about a lot. I thought it was fun to do a derivation because we got to use this Fourier transform table. We got to go through a lot of identities, and it worked in the end, even though I kind of like effed it up at the last minute. I feel like you guys still tracked. So now we see one of the key facets of the frequency response function. It governs how a sinusoid transforms through a system. So the frequency response function tells you everything you need to know about the steady state or forced response of the system to a sinusoidal input. Okay, so that's super powerful in and of itself, right? But then, just think how powerful it will be once we combine it with the powerful principle, god damn it, I used it twice, principle of superposition and the mighty Fourier series representation of a function as a superposition of sinusoids. So remember, we learned how to represent any periodic function as a sum of sinusoids, okay? And we just found out that if you have a sinusoidal input, the output is also sinusoidal, and the frequency response function tells you how the amplitude of that sine changes and how the phase changes, right? So we have this tool that allows us to construct a solution to any periodic input, not just sinusoidal input, but any periodic input, using just the frequency response function. It's pretty sweet. So we'll do that. Actually, when we come back from break, we'll be doing that. We're going to finish off this stuff before break with a lecture on Friday on Bode plots. So plotting the frequency response function. And then next week, I'm not going to hold you responsible on the midterm for being able to do problems related to what we cover next week, but we'll talk more about periodic inputs and all that. You should be able to answer on the midterm on Friday we get back. You should be able to answer questions that are conceptual regarding to that. So I won't expect you to be able to work out problems, but come to class next week, learn learn what we're talking about, because they might show up as a conceptual question on the midterm. High level stuff.